All right, just the last thing, you want to kind of keep an eye out for hints in the formula, right? This is all science. In general, us scientists are pretty logical and try to keep things clear. So let's take a look at an example of ethanol. Ethanol is the kind of alcohol you drink. So in your beer, wine, liquor, whatever, that's what's in it. And the formula for this is C2H5O. But there's many other compounds that have the same formula, right? Same compound, different bonding, those are isomers. And so there's many isomers of this. So when you write it as C2H5O, you're being ambiguous. It's not clear that you're talking about ethanol. And so it's not written like this. If you see a chemist write ethanol, they'll write it as CH3CH2OH. And so what you kind of want to do in these types of structures is read from left to right. And when you do that, the structure kind of becomes a lot more clear. So we want to put a carbon here, and then hydrogens are always terminal, so let's not worry about them yet. Then comes another carbon, and then an oxygen. And then we just fill in our hydrogens. So there's 3 of them here, 2 of them here, and then 1 here. And then if you think about Lewis structures, this oxygen is also going to have 2 pairs of lone pairs. And so this is the correct structure, the Lewis structure of ethanol. So you see how this going to this makes a lot more sense than the top one, right? It tells you, here's this CH3 group, here's this CH2, here's this OH. So there's the structure of ethanol, and you can see it's the same. Another example, acetic acid. This is just vinegar. Well, vinegar is basically diluted acetic acid. So its formula would be written as CH3CO2H, or maybe even, yeah, let's go with that. And so if you think about the structure here, again, you're seeing this kind of CH3 motif. Remember, carbon has 4 valence electrons, so it needs 4 more, so it tends to form 4 bonds. And then another carbon, and then basically an OH here, that's a common motif, and then another oxygen. And then if you count all the valence electrons and do everything correctly, you'd notice that this would also need to be a double bond, right? So that's acetic acid. So you can see how the formula will give you hints into what the structure is. Another hint, be careful of ions, right? So CH3CO2Na, this is sodium acetate. You can tell sodium is a metal. And so you should be thinking about ionic bonds. And so if you think about this structure here, it's overall going to have a negative charge on this oxygen, and this sodium is going to be positive. But then think about this structure even further, and you'll see there's actually a resonance structure here. We made one of these CO bonds a double bond and the other one a single bond, but really they're the same. And so each one of these bonds is really kind of a bond and a half. So be careful of ions, because you can have a mix of covalent and ionic compounds. Same thing for polyatomic ions. Something like NH4Cl is all nonmetals. So you may think that this is going to be a covalent compound. But if you think about NH4, that was one of our polyatomic ions. And so its Lewis structure looks something like this. And then the chloride is just hanging around there with a Cl minus. So be careful of polyatomic ions. Same thing with something like sodium sulfate, right? This is like kind of 2 Na pluses. And then this is an SO4 2 minus that's covalently bonded to itself, but then there's ionic interactions between the sodium and the sulfate. You want to take a look at the Lewis structure of sulfate too. It's pretty interesting and has a good number of resonance structures to practice with and some formal charge rules. So definitely do that one at least.